All right, let's go ahead and get started. I do want to welcome you to this worksheet. This is properties of gases. You are going to need a calculator for this one, so go ahead and pause the video if you don't have that, and we'll get started. Here we go. Properties of gases. Number one says the three most common state phases of matter are obviously solid, liquid, and gas. We've known that for a long time, probably since the 4th or 5th grade. So solids, liquids, and gases. We're going to concentrate on gases for this particular worksheet. Of these, the state which has no definite shape and no definite volume is gas. Obviously, gas is the phase that possesses the largest amount of space between the particles. It's compressible. It takes the shape of its container. Again, we've known that for a long time now. Number three, gases are so compressible because they consist mostly of empty space between particles. So if you think of the particles of a gas, for example, as being tiny particles like this, there are going to be many large spaces between those particles, and that's what's going to give gases their characteristic compressibility. So that's number three. Number four, the amount of a gas present can be measured by its volume, temperature, and pressure. So volume, temperature, and pressure are the three variables that we look at most closely when we're talking about gases. Name the SI or metric unit for each of these. The volume unit is the cubic meter or meter cubed. The temperature unit is the degree Kelvin unit, and pressure is measured in pascals. Pascals. All right, let's look at number five. Number five says convert the following temperatures into whatever they're asking for. And in this case, for example, they're asking me for 25 degrees Celsius. What is that in degrees Kelvin? The important thing to remember is that when you're going from Celsius to Kelvin, you simply add 273. So again, Celsius plus 273 will give you Kelvin. Notice that we have that little circle on the Celsius. We don't have that on the Kelvin. So to get from Celsius to Kelvin, simply add 273. Letter B, we have the melting point of iron is 1809 Kelvin. 1809 Kelvin. How do we get to degrees Celsius? Simply subtract 273. So 1809 minus 273 will give us 1536 degrees Celsius, and that'll do it for B. Letter C, we have 0 degrees Kelvin. By the way, that's called absolute temperature. We cannot get any colder than that in our universe. So 0 degree Kelvin, simply subtract 273. 0 minus 273 would be negative 273 degrees Celsius. Again, notice the little circle in the degrees Celsius, but no little circle in the Kelvin. The boiling point of xenon is negative 108 degrees Celsius. How do we get to Kelvin? Add 273 to that, minus 108 plus 273, give us 165 Kelvin, 165 Kelvin. All right, number six, the temperature is the measurement of the kinetic energy of gases. That's part of something called the kinetic molecular theory that we'll learn about a little bit later. One of the postulates of the kinetic molecular theory is that temperature is related to kinetic energy. The faster the particles are moving around, the greater the temperature, right? Number seven, the higher the temperature of the gas, the faster the particles are moving. So the faster the particles are moving, obviously the greater the kinetic energy, okay? There is a formula, by the way, that you will learn next year in physics, and it's this one right here. Kinetic energy is equal to 1/2 the mass. Obviously, for particles of gas, it's very small, times the velocity squared. So again, the faster the velocity, the greater the kinetic energy. Number 8, pressure is defined as force per unit area on a surface. So for example, let's just say that we have a container like this, and it has a number of particles in it, and those particles comprise the gas. We already have learned that there's a lot of empty space between the particles, but as they bang into the walls of the container, as they hit the walls of the container, they create pressure. So pressure is defined as the force, how much force per unit area, and that should be AREA. Let's make that an A right there, on a surface, just like that. So that is pressure. Number 9, the SI unit equal to 1 Newton per square meter is the Pascal. So a unit of force is a Newton, and a Newton applied to a square meter, or a meter squared, is a Pascal, and that'll do it for number 9. Number 10, because the unit of number 9 is so small, we often multiply by 1,000, we call it kilopascals. So kilopascal is a unit of pressure. Number 11, if two instruments used to measure the pressure are the barometer and the manometer. The barometer and the manometer, those are two instruments that we use to measure pressure with. Torricelli was the Italian scientist who invented a way to measure gas pressure using a column of mercury, the barometer, a column of mercury. Number 12, the gas pressure is caused by the collision between gas particles and any surface. So we've already mentioned that if you have some type of a container and that container has gas particles in it, the more gas particles that collide with the side of the container, the greater the pressure in the container. Number 13, use the relationships between units of pressure to convert the following. Show your work. All right, so we've got a couple of conversions that we're going to need to remember here. The first one is 1.00 atmospheres. So atmospheres is a way of expressing pressure. In fact, we are feeling approximately, in San Antonio, we're feeling approximately 1 atmosphere. We wouldn't feel it in Denver, for example, because there's less atmosphere. But the pressure that we feel every day is about 1 atmosphere in San Antonio, because we're about at sea level. So 1 atmosphere is equal to, well, 760 millimeters of mercury. Here's the math. We have 1.00 atmospheres over 1 times 760 millimeters per atmosphere. We'll cancel atmospheres and we're left with 760 millimeters of mercury. That'll do it for 13A. 13B, it says 745 torr. So we want to convert that to kilopascals. So we're going to start with what we know, 745 torr over 1 times, this is the conversion, 101.325 kilopascals per 1 torr, or excuse me, 760 torr. By the way, both of these are equal to 1 atmosphere. So 1 atmosphere is equal to 101.325 kilopascals divided by 760 torr. I could have gone to atmospheres and then gone to kilopascals, but I elected to do it this way. So torr over torr will cancel, and I'm left with kilopascals. Multiply 745 by 101.325, divide that by 760, and I get 99.3 kilopascals. Letter D, we have 98.5 kilopascals is equal to how many atmospheres? Here's what we're going to do. We're going to start with what we know, 98.5 kilopascals over 1 times kilopascals over kilopascals times atmospheres, right? So what we're going to do is we're going to recognize that 1 atmosphere is the same as 101.325 kilopascals. We've already mentioned that. We'll cancel kilopascals with kilopascals, and we're left with atmospheres. 0.972 atmospheres then is our final answer, and that'll do it for 13D, and that'll do it for this worksheet. I'll see you on the next one. Thanks. Bye-bye.